All right, so one more lesson looking at kinematics, which looks at, we're going to look at two different things here, one of which should be relatively familiar, which is looking at acceleration in terms of time. Where things will get a bit harder is where we look at velocity and acceleration in terms of displacement or something else. But first, let's look at this question here. It has a matrix in it or a vector in it, but it's fairly quick. This is the velocity, and it's given with a column vector. And so that first element just represents perhaps its velocity in the x direction, the other was in the y, and we're given a starting point. So if I want to find the position vector after 4 seconds, first let's find the general position vector, which means I need to find the antiderivative of each of these separately. It's not a big deal at all. So for part one, my position or my displacement would be the antiderivative, the first element of t squared minus t. So that's t cubed over 3 minus t squared over 2 plus some constant. I'll put c1 because there's going to be another and most likely different constant below it. I want the antiderivative of t squared plus 2, which is t cubed over 3 plus 2t plus some other constant. So again, you can see where these come from. That's it. We also know the initial position is at 1 and 3. So we can now use that to solve for each of those constants. So I know when time is 0, the position is 1, or the displacement is 1. When time is 0, the position is 3. And so let's quickly solve each of these separately. That means I know that first equation, if I replace t with 0, it's going to equal 1. And so I get 0 cubed over 3 minus 0 squared over 2 plus some constant equals 1, which means that constant must equal 1. And similarly for the other part, I get 0 cubed over 3 minus 0 times 2 plus some other constant equals 3. In this case, that constant must equal 3. So now I know my position vector, now I know my displacement function. It is just this here, but instead of C1, I should say C2 there. There we go. I have 1 and 3. And so now all I need to do to find its position after 4 seconds is go back here and replace all these t's with a 4, because remember again, we know those constants now. Pretty familiar idea, just a vector just means that we have 2 for the price of 1. So when t equals 4, we have 4 cubed over 3 minus 4 squared over 2 plus 1. And we have for the other element below it. And if you just do a quick bit of work, I'll leave these as fractions in lowest terms. You get 43 over 3 and 97/3 for the other. So there's our position. The units these are in meters. Remember, especially with kinematics questions where you have multiple functions all representing all having different units, but are all related to one another, we want to always try to remember to include units. All right, find the acceleration at 4 seconds. Well, let's just differentiate this. And again, substitute t with 4. Should be faster, so the acceleration function, I guess I should really say differentiate these here while we still got our variables. I think you get the idea. I'm impatient because I think we got it. My first piece will be 2t plus 1. The second one will just be 2t. When we differentiate this, and again, let t equal 4, and we really quickly get our acceleration at that point being 7 and 8 meters per second squared. And there's our answer for that. Just keep in mind, any column vector we could also write with the components I and j. I'm not a huge fan of it, but who cares what I think. And so you could also write this, assuming the screen stops fighting me. You could also write this as 7i plus 8j meters per second squared. Just as good. Doesn't matter what you use as long as you understand both. All right, that section, which in Cognity is 5.133. There's some more challenging questions in there, but they're fairly familiar, these sort of acceleration, velocity, displacement questions. They're very important, but what you're probably going to find more challenging are the questions here, mostly because they're less familiar. It's not a big part of it, but I want to spend more time on this because it's less familiar and surely more challenging. What I have here is a particle moving in a straight line. That's pretty familiar. The displacement, though, after t seconds is given with this function here that is not, it's not solved for t or solved for s. Now, it would be pretty easy to solve for t, just divide everything by 3, but usually we would have displacement as a function of t. And we can't really isolate s so nicely here. We can't really isolate s. That said, this is what we call an implicitly defined equation. And notice the first thing I ask for is the velocity as a function of position. That's the first thing I want. Now remember, velocity is the derivative with respect to time of displacement. So even though this function we see here is not solved for s, we can still differentiate with respect to time, and that'll tell us the velocity. And so it's called implicit differentiation. We've done it a little bit, especially with our related rates questions. So for part 1, I want to take this function s squared plus 2s equals 3t, but I want to differentiate everything with respect to t, keeping in mind that s, the displacement, is itself a function of t. Otherwise, I'd have a whole bunch of constants with derivatives going down to 0. So with that said, if I look at this, this first part here, the derivative of s squared with respect to s is 2s times the derivative of the inside function, the derivative of s with respect to t, which is s prime, or ds dt, which, keep in mind, is velocity. Let me do the same thing for the next part. For here, differentiate 2s with respect to s is 2, multiplied by the derivative of s with respect to time, with is s prime. That's the trickiest part. On the right-hand side, differentiating 3t with respect to t is just 3. Well, notice, again, as I mentioned, this s prime here, this s prime here, that is a derivative of s with respect to time. That is velocity. And so if I can isolate those, which I can quite quickly, I can find the velocity. But notice it'll be the velocity with respect to s, not time. There's no t variables here. So let's take this. I'll keep going sideways to give myself some space. Let's let's factor out s prime. You get 2s plus 2 as a factor equals 3. Divide both sides by 2s plus 2. You get s prime equals 3 over 2s plus 2. Keep in mind that is velocity. So that's my answer. Notice right here we have the velocity, right? Remember, s prime with s displacement with respect to time is velocity. So we found the velocity of this function, but as a function of displacement. And usually we think of velocity. Well, velocity by definition is the change in position over time, but we have it here defined in terms of its position, which is a different idea. Hence, I said I want to spend more time on this. All right, that is velocity right there as a function of position. So what's the velocity when the displacement is 1 meter? This should be really quick now, because this here tells me the velocity if I know any particular position. So I can now take that equation there and replace s with 1, and that'll be it. And so for part 2, I can say velocity equals my previous function, 3 over, I'll just write it out again because it's off my screen. But this time I want to replace this with 1 because I want to know what its velocity is after 1 second. So I just get 2 plus 2 in the denominator. So I get 3/4 meters per second. So not after 1 second, when the particle has a displacement of 1 meter, its velocity is 3/4 meters per second. So what's the acceleration? Now acceleration, again, is meters per second squared. It's the derivative with respect to time of velocity, but I don't have the velocity with respect to time here. This is where this relationship up here comes in really helpful. That acceleration is equal to a whole bunch of things, but the new part is it's the same as the derivative of velocity with respect to position times the velocity. So that's going to come in handy here. So let me write that down here. That's a relationship that, again, is most likely new. So I'm going to write acceleration equals dv ds times the velocity. So dvds is it will be the derivative of this up here with respect to s. So that's fairly familiar to do something like that. And so let me just take this first before I start differentiating it. Let me rewrite it in a form that I would prefer to use, which is writing it as 3 times 2s minus 2 to the power of negative 1. And I would rather differentiate this than using the quotient rule above. And so if I differentiate that, I'll kind of keep everything on my screen. Then that will lead me to using the power rule, I get negative 3 times 2s minus 2 to the power of negative 2 times the derivative of what's inside the power. So derivative of 2s minus 2 is just 2. So everything we see there, that is the derivative of v with respect to s, which is the derivative of what I just was looking at back there. So now to find acceleration, I need to take that and multiply by velocity. Well, velocity is what I just have highlighted in multiple places up here in blue. Oh, that's my eraser. There we go. So I'm just going to take, oh, that's my eraser. Take 3. I'm going to take that there and substitute it right there. Or multiply dvds by that. And so let's take what I just wrote down and multiply this by what I had before. I'll write it as a fraction, write it by 3 over 2s plus 2, right? That's the velocity we found in the last question. The velocity with respect to position, but it's still velocity, and its units are still meters per second in this case. So let's clean this up a bit. Everything you see highlighted in green is the same as negative 6 over 2s minus 2 squared times 3 over 2s plus 2. Oh, I have a minus 2. Oh, you probably hate it when I do stuff like this. I hate it too, trust me. I don't know where that became a minus. It just did. Now it's not. And so this should be a plus. That should be a plus. And then so I have negative 18 in my numerator, and I have 2s plus 2 to the power of 3 in my denominator. So that's the function for acceleration as, you know, it's acceleration as a function of displacement. I want to know what is the acceleration after 1 meter. So I just need to take this s, change it to a 1 again, and we should be done pretty quickly. So let t equal 1, and so that leads me to negative 18 over 2 times 1 plus 2 cubed, which is negative 18 over 64, which reduces to negative 9 over 32 meters per second squared. So everything here was a lot more unfamiliar than the type of kinematics questions we've seen earlier. And this particular question here really hinged, especially the later parts, on this relationship here, especially how acceleration is the same as this. And that is the new part here. And it's almost certainly one of the most challenging parts, which leads us to the last question. Another tough question. Hopefully I get my negatives and positives right here. A particle is moving along a straight line. The acceleration is given as a function of velocity, as acceleration is negative 1 plus v in brackets. And the initial velocity is 1 meter per second. So what is an equation for the rate of change of velocity with respect to displacement? So what does that mean? The rate of change of velocity with respect to s. That means I'm asking what is dv ds. That's what I'm asking for. In the last question, that's what we figured out right here or here. Well, how do I figure out that in this case? I don't actually have my velocity function as a function of position. Well, let's again go back to this relationship here. Acceleration, which we do have, is the same as dv ds, which we're trying to find, times velocity. So let's write that down again. So acceleration equals the derivative of velocity with respect to position times the velocity. Well, we know the acceleration. The acceleration is negative 1 plus v. We're trying to figure out dv ds. And we know the velocity. It's just v. It's the same variable we see right there. Which means I can isolate dv ds pretty quickly, divide both sides by v, and I have the first part done. So I can see the derivative of velocity with respect to position must equal negative 1 plus v divided by v. I could distribute the negative, but I won't because I don't know. Why? That's it. There's my first answer. That is the derivative of v with respect to s. The second part is, what's the rate of change, which means the derivative of displacement with respect to velocity? That's the other way around. It's this the other way around. It's not dv ds, it's ds dv. So how do we figure that out? I want to find the rate of change of displacement with respect to velocity. Well, it's quite nice. If you just look, this here is the reciprocal of this, which means my answer will be the reciprocal of that. I like reciprocals. And so that means this will be just negative v over 1 plus v in my denominator. There, that's it. That said, and I want to use this. This is the hardest part. Find the displacement between the starting point and the position when it comes to a rest. All right, so keep in mind this equation here. This shows me the displacement, the change of displacement with respect to velocity. I want to think about what's the displacement. I want to actually now think about just displacement. Well, this is the derivative of displacement. So if I want to think about just displacement, I need to think about the antiderivative of this function we have right here, which means I want to think about the indefinite integral. So for part 3, in this case, the indefinite integral of ds dv with respect to dv, that will tell me the position function. Or a little more specifically, if I find the indefinite integral of negative v over 1 plus v, because remember, this here is ds dv. And again, dv. Then this here, the antiderivative of this, the indefinite integral of this, will be my position function. And so I need to think about this. So how can this here represents my position. So now how can I use that to find the change in position, the displacement between the starting point and when it came to a rest? Well, let's think more about this integral here. I want to make it a definite integral. So let me write this down. Negative v over 1 plus v dv. So here v is velocity. And yet I know this whole thing altogether represents position or displacement. So what I want to do is think about, okay, I want to find what's the change in position or the displacement from the starting point to when it came to a rest. Well, at the starting point, we see that it had a velocity of 1 meter. And keep in mind, everything here is a velocity. And when it comes to a rest, that means the velocity is 0, which means I want to integrate this starting at 1 down to 0, when velocity starts at 1 and goes down to 0, which means I can make this a definite integral if I put a 1 at the bottom and a 0 at the top, because then we are starting at 1 and going down to 0. And this here I know will be the same as the initial position minus the position after not 1 second, but when the velocity is 1. That's it. That's what we're trying to find. Now, I don't actually need to figure this out. I just need this, which I can do on my GDC quite nicely. And so we want to use our GDC here. And I should really quickly get to about 0.307. If you're getting a negative number, you probably have your integral the wrong way around. You probably have a 1 at the top and 0 below. Keep in mind, again, it does say we are starting with a velocity of 1 meter per second and coming to a rest. So that's why I have it like that. And this is, keep in mind, a position, so this should be meters is our answer. All right, so just before I wrap this up, just keep in mind, while these last types of questions are the hardest part, they're not a hugely important part of the course, but because they're pretty new, I wanted to put a bit more emphasis on it. And again, I apologize for those negatives earlier. You're used to it, I think. I don't know.